So I haven't made a video in a while, so here we go. Linear approximation, otherwise known as tangent line approximation, basically says if you have a curve, the white one, f of x, here's my f of x, I can use the tangent line of some known point, which we'll call C here, and this is my tangent line, the blue line, to generate a good approximation of what this value is. As long as delta x, which is the distance between these 2 points, is not very big, then this distance will not be very big. Okay? So the way this works is m, slope. We know we don't really say slope in calculus. We say the derivative, so f prime of c. And the slope that you learned in Math 10 is y2 minus y1 over x2 minus x1. y2, we are calling that f of c plus delta x. There it is right there. Minus y1, which we're calling f of c right there, over x2, which is this one, c plus delta x, minus x1, which is c. Obviously, those c's go away. You're left with delta x in the bottom. The numerator, you have f of c plus delta x minus f of c, and all of that equals f prime of c. So if I multiply the delta x up, I get f of c plus delta x minus f of c is equal to f prime of c delta x. Sorry for this. Oh, wow. Sorry, everybody. There it is. Okay. And then I'm going to move over this f of c, and I get f of c plus delta x is equal to f prime of c delta x plus f of c. That is the linear approximation formula that he showed you. I never remember this formula. All I remember is use the tangent line at a known point. So for example, because this is really just y is equal to, instead of writing f prime, mx plus b. That's really what you're doing. But I can show you how to do it both ways. So for example, if I say, what is the square root square root of 16.5? Okay, well, let's use the linear approximation formula. Let me write it out here. C plus delta x is equal to, C is what you know. It's a known one. Delta x is obviously the difference between your known and what you're trying to determine. And c plus delta x, so that would be 16.5. So obviously we're going to use the square root of 16. Okay, we know that that is 4. Our function is a square root function, so it's root x, which is x to the 1/2. I need to get the derivative. So f prime of x is equal to 1/2 x to the negative 1/2, which is 1 over 2 root x. The c value is a nice easy square root, which I said before was 16. So f prime of c, or f prime of 16, sorry, is equal to 1 over 2 root 16, which is 1/8. F of c is f of 16, which is root 16, which is 4. So then I just plug it in. I go f prime of c, which is 1/8. The delta x is how far my known is from what I'm trying to find. So from 16 to 16.5, that is 0.5, plus f of c, which is 4. 1/8 plus times 0.5 plus 4 is 4.0625. And that is your answer. And that's it. That's all you do. So if you know this formula, or this formula, I guess, and you should remember C is what you know, a nice, easy, if you're doing a square root, a cube root, fifth root, doesn't matter. You pick one that you know and is close to the one you're trying to find. You don't want delta x to be too big. If delta x is too big, it doesn't apply, because you could see from this graph, it's linear, so it's going up here, and the square root graph is curving like this. So the further you are away from your point, the bigger the error is becoming. All right. Page 237, numbers 37 and 39, just a couple of questions to practice there, and then I will do differentials in a sec. See you in a bit. Okay, everybody, welcome back to differentials. Differentials are basically the same thing, except we use differentials when we're doing a lot of error measurement in science. Okay, so if you start with y is equal to f of x, just some function. If I take the derivative of y, I can say dy dx is equal to f prime of x. That's really back in beginning of chapter 2. Now, just to show that this is the same as linear approximation, I'm going to go off on a little tangent here. I can say f prime, like we saw on the other side, is the slope, which is y2 minus y1 over x2 minus x1. And then I could continue, because that is this statement right here, and then we could follow this to get to this formula here. Okay, I'm not going to do that. What I'm going to do is I'm going to say, if you've taken physics, y2 minus y1 and x2 minus x1, those are deltas. That's delta y over delta x. F prime of x. So now this and this are very, very similar, right? So this will become important in a sec here when I talk about error measurements. So before we get there, if I take this dx here and multiply it up, I will get dy is equal to f prime of x dx. This is a differential, or differential form. Okay? When you've written it as dy is equal to f prime dx. And you'll see later on in this course we'll solve what are called differential equations, and they're written in this form. Now, I just showed you, using this, rewriting f prime as y2 minus y1 over x2 minus x1, getting delta y over delta x. That means that delta y is approximately equal to delta x, or sorry, dy, and delta x is approximately dx. Okay, so this is essentially coming into error measurement, because delta x is, if you think about it in science terms, this is a very practical way to think about it. That's the error, that's the plus or minus error that you have when you do a measurement. So if I have a question that says the radius of a circle is measured to be 16 centimeters plus or minus 0.25 centimeters. Okay, that's your error, because nothing is 100%. What is the propagated? All that means is what is the scaled error, I guess. error of the area of the circle. Essentially, they're saying this is delta x. What is your delta y? I.e., delta x is dx and delta y is dy. Okay, so I'm talking about area of a circle. Area is pi r squared. We're talking about differentials, so take the derivative. That's all you really know how to do right now. So dA, the derivative of a with respect to r is 2 pi r. That's it. We want to write it in differential form. So I multiply this dr up to the other side. So dA is equal to 2 pi r times dr. That's differential form. And I call this delta x. It's actually dr in this particular case. All right. It's that one right there. So all you do is the dA, which is delta A if you want, is 2 pi r is 16 centimeters times dr, which is plus or minus 0.25 centimeters. If you multiply that all out, you end up with 8 pi centimeters squared, and it's plus or minus. That is your dA. That is the propagated error of the area. So if you're off by 0.25 centimeters in measuring your radius, your area will be off by plus or minus 8 pi centimeters squared. So it's a big error. Now, what is that in terms of percentage? If you want to measure the percentage or the relative error, so the relative error is going to be the delta A, or we'll call it dA. It's the propagated error, this thing, divided by what the actual area of the circle is. dA, we determine that over here, 2 pi r dr. Area of a circle is pi r squared. That cancels, that cancels, that cancels, that cancels. You're left with 2 times dr over r. 2 times dr. dr was 0.25 plus or minus, divided by the actual radius, which was 16 centimeters. You punch all that in, you're going to get plus or minus 0.03125. Now, that doesn't really mean a lot, so that's called the relative error. But what is that as a percentage? Well, multiply by 100%, and you get plus or minus 3.125%. That is the percent error. There's a couple questions in the book. Did I give the page number before? I did page 237. Numbers 25 and 27. Yeah, I'll go over this at the beginning of class tomorrow. Good luck. See you tomorrow, peoples.